Okay, thank you very much. First of all, I'd like to thank the organizers for this very enjoyable and interesting conference and for giving me the chance to present our work here. And this talk will be called Fluxes, Warping, and you see this has entered a little bit later, Constraints in F-theory. It will be essentially based on three works which appeared in last half year or so. This is a paper with Hirotaka Hayashi, who's also in the audience, which is about chirality and flux. Then a paper with Dennis Klebers, who is in Penn postdoc, and Maximilian Porechkin in Bonn. And then maybe if I have time in the last part, I will tell something about the paper with Worty Taylor, which appeared recently. Let me start with some introduction and motivation, which will be a little bit different from what Miriam and also what was used yesterday, but it will be a bit more landscapey in some sense. First of all, we start with some fundamental theory, let's say F-theory for this talk, and we want to compute the Wilsonian effective action. So what does that mean? That means that we actually have to integrate out massive states. We not only drop them, but we actually have to integrate them out to derive the couplings in the effective theory. Then what we can hope for in such a string compactification is that we can classify the core data of a given compactification by some integer numbers. In an ideal world, that would be like this. We have some geometric data which determines the bulk geometry, some brane discrete data, and some flux data. Okay. Then at the end of the day, we have some effective action, which can be, of course, very complicated, and the field dynamics is then determined by some potential, and we can determine four-dimensional vacua and do some phenomenology. That's all I will say about phenomenology in this talk, mostly. Okay. So if we want to address such a question, it's good to look for a unifying setup which is very general, so that we can ask very general question about, so to say, the landscape of possible string effective actions. Of course, it would be nice to unify the brane physics and the geometric aspects. Okay. The ideal setup probably would be 11-dimensional M-theory. Right? If you would have a full understanding of that. For example, the key example here is that the D6 springs emit a geometric interpretation in M-theory. So it would be a unification of this n geometric and the n brane into one unified geometric object. However, there is a major drawback, namely that if we want to study a four-dimensional effective theory, we have to compactify on something which is seven-dimensional. We heard on Monday that this can be done, and these are these G2 compactifications. However, the construction of such manifolds and the study of singularities of such manifolds is very hard. And the basic reason is very easy to explain, because we don't have the power of complex geometry or holomorphicity at our hand. F-theory provides a very nice way out. Namely, it unifies, in this case, seven-brane physics with the bulk physics, with the geometric part, but we can stay in the context of complex geometries. And this very nice gut constructions which appeared in the some years ago, they actually use heavily the fact that we have this kind of dimensional hierarchies just jumping between even dimensions. So we can use complex geometries, and this was essentially the reason, in addition that we can have guts in F-theory, that this came up in F-theory. A second thing I want to stress here is that, of course, for many years now people studied moduli stabilization, and mostly in the context of F-theory compactifications with fluxes. So these large numbers of vacua, they came out of these F-theory analyses. So, what are the obstacles to study F-theory? Well, in contrast to string and M-theory, we don't have a 12-dimensional F-theory effective action. And the fundamental formulation is also poorly understood. So we have to find a way to nevertheless address these questions in F-theory and ideally to compute the full effective action and study corrections and so on. We have heard that there are various limits where this can be done. So there's the weak coupling limit, where we end up with string perturbation theory and can study D7 branes and O7 planes. In the previous talk, or also in the last days, we heard that F-theory heterotic duality is very powerful, but it's a specific limit within the full setup of F-theory compactification. And local limits, local geometries are also very powerful. However, to my belief, the only known way to extract generic features of F-theory effective action is using its formulation via M-theory. And what I want to point out to the non-experts is, so if you hear something like G4 flux and M5 branes, this kind of limit between M and F-theory should always be understood. Because, I mean, here it's pretty obvious, but also a G4 flux in a generic F-theory compactification, it is not a priori clear what that means. It needs some interpretation. And that's actually the goal of my talk. What I want to tell you is that this interpretation is not always straightforward, right? So there are unexpected identification between the various things. For example, I want to tell you how to derive the 40 chiral index using M-theory G4 flux. Okay. In the second part, I want to derive corrections to the F-theory gauge coupling function using the M-theory dual. And in the third part, I will not derive something, but I will stress some idea how one can use these effective action to actually learn something potentially interesting about string theory landscape or string theory in general. So what is the message which you should take home is that F-theory effective action can be reliably computed, right, by reliably studied. Bulk and brane physics unified in a generic n=1 setup. So the orientifold setup, they are very nice, but they are coming somehow by a truncation of some n=2 setup, right? But this is a really an n=1 setup, and the M-theory origin of the various F-theory effects can be unexpected. I hope to convince you of this. To get started, I really have to review this link between M-theory and F-theory briefly. We heard already what F-theory is. It's kind of this SL2Z symmetry is interpreted as some symmetry of an extra 2 torus, and the tau, the dilaton axion, is the complex structure of this 2 torus. Right? Here we will consider 4-dimensional F-theory compactifications. So it will be on a Calabi-Yau 4-fold, and this 2 torus can pinch. Wherever this 2 torus pinches, this tau becomes singular. Wherever the tau becomes singular, there must be some source. This is the location of the 7 branes. So that's how the 7-brane physics is included. But we are inside of complex Kähler geometry, and we can have n=1 supersymmetry if this is a Calabi-Yau 4-fold. So this I already explained. So now how do I link this to M-theory? I don't have a 12-dimensional effective theory. It would be nice to have that, but it's also from a conceptual point of view, it's not clear if it exists at all. But what we can do is we can go through this relatively simple limit at first. Namely, we start with M-theory on a 2 torus times some 9-dimensional space. Tau is the complex structure modulus of this T2, as I already mentioned. We have some volume, and we look at the A and B cycle. So if I make the A cycle small, then I go from M-theory to type 2A. We all know that, of course. But now if I perform a T-duality on the B cycle, I would go to type 2B. In other words, if I shrink the volume of this torus, I better go to the T-dual picture, right? Because I make this torus small, and then I better go to the T-dual picture, and I end up in type 2b. And indeed, following through this T-duality and M-theory type 2a duality, tau is indeed the dilaton axion. It better be, otherwise we are on the wrong track. However, what also happens if I make the volume small, I actually grow an extra dimension on the other side. So it's a trans-dimensional duality, right? So it's while this would be a compactification to 9 dimension, the type 2b setup would be then a 10-dimensional setup. This all would be kind of boring if this just would be a torus, but the nice thing, it can be generalized also to the non-perturbative objects, to the branes. I will come back to this. How do we now deal with the M-theory geometries or the F-theory geometries? Now you can always change back and forth. Well, in M-theory you can do something which you cannot do in F-theory, namely you can resolve the singularity which describes the non-abelian gauge symmetry on these branes. This you can do in M-theory, and in M-theory you can then use compactifications on a resolved Calabi-Yau fourfold. Right? In M-theory this is completely fine, and there are numerous examples of such resolved fourfolds and threefolds. Yeah, there exist large lists with all kinds of gauge groups, huge gauge groups. And on this resolved Calabi-Yau fourfold, this geometric part and the brane part is nicely unified in topological information about this fourfold, about this resolved fourfold, in intersection numbers and so on. Okay. But what does that correspond to in this M to F theory duality? And now we can understand why this is only possible in M theory. If you look closer, the resolution corresponds in the type 2a picture actually to moving the branes apart on this extra circle on which we will T-dualize later to go to type 2b. So in type 2a, these are 6 branes, and these 6 branes have 1 dimension less, so they are a point on the circle, and we can move them apart, and moving them apart corresponds to blowing up in M theory. This, from the D6 brane picture, this is very clear that this means that we go to the Coulomb branch of the gauge theory. In the M theory picture, this means also going to the Coulomb branch, and in fact, if you remember, if I compactify M theory or 11-dimensional supergravity on a smooth resolved manifold, I just have U1 symmetries, right? So we are in the Coulomb branch of a 3-dimensional theory here. So every state has to be integrated out automatically to have this smooth geometry. So for example, M2 branes on the resolution P1s over this gauge singularities have to be integrated out. And in fact, in this duality, they correspond to massive W bosons in this breaking of the gauge group. M2 branes on the resolution P1s over the intersection of 2 singularities, they actually correspond to massive matter multiplets. Remember, I'm in the blown up phase, so they're always massive, these M2 branes. Only if I go back to the singularity, these fields become singular. The elliptic fiber itself, I told you, corresponds to this 2 torus, and there will be massive Kaluza-Klein states. And to be honest, all these things can also mix. I mean, So in other words, in order to determine the Wilsonian effective action in 3 dimensions, we have to integrate out these modes, including the Kaluza-Klein modes. And since it's an even-dimensional theory, they all will play in odd-dimensional theory, a 3-dimensional theory, they will all play a role. So what we will do is, F theory on a singular Calabi-Yau fourfold with some gauge bundle, some flux bundle, gives a 4-dimensional effective theory which we want to determine with some non-abelian gauge symmetry. We put this on the circle, we push this to 3 dimensions, and we go to the 3-dimensional Coulomb branch. Then we determine this effective theory by computing the effective actions, including certain loop corrections. We compare this to M theory on the resolved Calabi-Yau fourfold. Here we know that we are allowed to switch on something called the G4 flux, just the field strength of the M-theory 3 form. And then we get a 3D n equals 2 effective theory with only abelian gauge symmetry. We compare these two and we try to backwards infer data of this unknown 4-dimensional theory. That's the limit, that's what we will do, and that's what we did in these works over the last years. So why is it unexpected? Why is this? Why is that so non-trivial? So what I did some time ago in 2010 is to look at the leading Kähler potential and so on, and this was fitting very nicely with the expectations. But there were some corrections which were not understood by this time. Okay, and it comes in particular once we include fluxes. And this is what I'm going to address now. Fluxes in F theory, in addition to setting a new record of number of F's in the title of a slide. So, what I want to point out is that the specification of fluxes in F theory is very hard. And we will hear more about this in two talks today by Sakura and by Timo. They address, I guess, some M theory, some maybe some spectral cover, and some decoupling aspects. So this is some advertisement. What I want to do here is I want to look at the M theory dual model on the fully resolved Calabi-Yau fourfold, and when I do the resolution, I get new resolution 2 forms, and the geometry becomes richer because I have new intersection numbers, for example. But the gauge group is broken. I can do that equivalently, including some extra U1s. So I get also some new resolution 2 forms and have some new U1s. The M theory fluxes on this resolved geometry can now take the following form. They can be wedges of this resolution 2 forms. And what I want to point out is that these fluxes on the singular geometry are strange, right? Because these are fluxes which actually these are 2 forms which are not present on the singular geometry. In order to lift such fluxes to F theory, these G4s have to satisfy certain vanishing condition, and they are subject to quantization condition, as will be discussed in Raffaele Savelli's talk. So now what people wrote down is, and studied intensively, is we want to understand how we compute the chiral index, the net number of chiral fields in such an F theory setup. Right? That's the most basic question we can ask. And how do we do that if we have no fundamental formulation? Well, we could write down such an expression saying that the G4 flux integrated over some surface is the chiral index. But how do we understand physically that such a thing has to exist? And the answer which we have given is that in the 3D Chern-Simons theory, this can be actually understood. So how does that work? If I take a 4-dimensional theory, n equals 1, put this on a circle, there will be no such Chern-Simons terms where these are the indices of the Cartine U1s. They are just absent, they are 0 classically. However, they will be generated at one loop, and they will be generated by massive fermions. But what are the massive fermions? The massive fermions are all the things which were charged under the gauge group, right? And now become massive because we have gone to the Coulomb branch. So they will exactly be the 4-dimensional charged matter fields. Okay. This is the expression which one can compute. It's a one-loop computation correction to this classically absent Chern-Simons term, and you see that there's some here some weights appearing, and this is the sign of some volume of some cycle appearing. So this is what you should keep in mind, and this is the expression which will lead us now to derivation of this chiral index formula. Namely, in M theory on the resolved Calabi-Yau fourfold, this Chern-Simons term is not absent. It's actually there if I switch on G4 fluxes. So if I switch on G4 fluxes, this Chern-Simons term is there. And so we can match these two things and find a link between the flux and the representations in 4 dimensions. In an ideal world, this would allow us to give us the number of fields in each representation, but since we are not in an ideal world, so you see the sign appearing here, and in fact, this, if the conjugate representation appears, there comes a minus sign, and so only the chiral index can be inferred from this one loop computation. Okay. But the nice thing is that this allows us to give a computation of this chiral index using the M-theory dual geometry. We studied this at examples, once without U1, some SU5 example, and also the ones with U1s, and I guess we will hear more about these kind of constructions later on today. The nice thing I want to point out is that we are now on the way to find an algorithmic implementation. Because we are on resolved geometries, we can look at Kreuzer-Skarke lists for fourfolds, or we have to construct a larger sample. And it would be very nice if maybe people here in the audience get interested and have the technical skill to actually start now to implement some search algorithms to go through global models, study gauge groups and the chiral spectrum in this example. So that was the first unexpected thing. You have to include one loop effects on the, if you want to study resolved geometries. You have to study resolved geometries if you want to scan through some big lists or you want to make model searches. The next unexpected thing, warping and the gauge coupling function. Let me switch gears and go to another aspect of the effective action. Namely, I want to study the gauge coupling function of 7 branes, and now want to ask, can I compute alpha prime effects using M-theory? Okay. That's an example. An example is the gauge coupling function, which is just a classical volume, and then there's some correction due to fluxes. Right? If I switch on fluxes on these 7 branes, we know there's a correction which is linear in this Dilaton axiom. For simplicity, I will just consider fluxes in the Cartan of the simple type. So whenever you see the symbol n, it means this flux. Okay. Can we generalize this to F-theory using M-theory? So in other words, can we derive these alpha prime corrections? Well, at first it sounds strange, right? Because this is an F to the 4 term, and the M-theory, so 11-dimensional supergravity, has only 2 derivatives. How can we how can such an expression appear? Well, the answer is it's a back reaction effect in M-theory. So the back reaction effect is actually like this. We know that the Becker-Becker solution involves actually a warp factor. So the M-theory compactification to 3 dimension has a warp factor. And the point is this warp factor is important because as soon as I switch on fluxes, this warp factor will be sourced. If I switch on fluxes on the brane, the warp factor will be sourced near the brane. What's the goal? We want to solve the warp factor equation explicitly near the 7 brane. And the point will be, even if I switch off the warp factor in F-theory, we have to include the warp factor in M-theory. Essentially because of this extra circle. So the duality proceeds as follows. I explained this already. These 7 branes go to the 6 branes. We can move them apart. And in M-theory, the geometry, the lift of this setup with the 6 brane will be actually a periodic multi-centered Taub-Nut space over S where this brane is wrapped. So it's quite a fancy geometry. Here you can, it's not an actual photo, it's a picture which I have drawn. And this is here what we will consider as a local Calabi-Yau fourfold. Okay? So it will be such a multi-centered infinite area of Taub-Nut spaces, which is kind of here the centers of this Taub-Nut space. and this will be periodically extended infinitely many times. Okay. The nice thing is we want to solve the warp factor equation, but we don't know the Calabi-Yau metric. Okay? But in this local geometry, we actually know the metric using the Gibbons-Hawking metric, but we can extend that to an infinite area, like in electrodynamics. You make an infinite line and then you make a Poisson resummation, and what you actually find is that these potentials which determine the metric can be actually given explicitly. Quite remarkably, or luckily, this precisely starts with a logarithm as expected from a 7 brane. If you don't resum, it starts with 1 over r, like for a d6 brane. So this is how the logarithm appears after Poisson resummation. You can match this with the torus vibration at some cutoff, and then you find that the dilaton indeed goes logarithmically. Given this metric, we can construct some harmonic forms on this multi-centered Taub-Nut space, and this is the nice thing, where if we now switch on the 4 fluxes along these harmonic forms, or F2 fluxes on the S, on the brane, on the 7 brane Volt volume or 6 brane or Taub-Nut space, is we can solve this warp factor equation explicitly, right, by using essentially this this geometry. So it's a very, very neat result where you can actually perform a warped reduction with an explicit form of the warp factor. And now if I plug this back into the 3-dimensional theory, you see that the warp factor equation can be evaluated, and here is this n appearing, this flux squared. This determines the gauge coupling function. So in other words, we can use this explicit solution to compute corrections to the warp factor, to the gauge coupling functions, leading order at GS, but we also can infer GS correction. So this is the way how in M theory we can compute the corrections, the alpha prime corrections to the gauge coupling function in a very neat way, I think, which has this explicit solution. In the last 3 minutes, 5 minutes, I will say, right. So what I told you so far is like 2 aspects which we solved in the which we addressed in the last half a year or so. How one derives the effective action using the M theory dual. There's much more to come, I believe, and it's a very exciting question to systematically go through all the corrections. Now I switch gears once again, and I say I have the effective theory. Which terms should I look at? So this will be about this work with Worty-Taylor. And here's the basic idea. In 6-dimensional F-theory compactifications on the Calabi-Yau 3 folds, they are very neat, because in 6 dimension you have a lot of anomalies which fix many data of your effective theory. We worked out the effective action, and you can go. You don't even have to take a limit. You can actually do the match precisely between M theory and F theory. But so you have strong constraints from anomalies in the effective theory. To what do these constraints map? Well, they map in F theory to the geometry of the internal space. Right? For such an elliptic vibration, these are just satisfied, these constraints. If I give you an elliptic vibration, this will be an anomaly-free theory. So in other words, we can relate terms in the effective action and, for example, the spectrum, as we know from anomaly cancellation. And this is encoded in the singular elliptic vibration, or resolved elliptic vibration. Now we go to 4 dimension and we can ask, can we do something similar there? Well, in F theory, we have again topological properties of consistent elliptic vibrations, but we don't have this anomaly interpretation. So we can ask the question, can we relate terms in the effective action to the spectrum despite the fact that we don't have anomalies? And are there universal constraints? And what we pointed out is that a nice testing ground are actually these kind of topological terms. They can be linked to anomalies via four-dimensional Green-Schwarz if these axions are actually gauged, but they don't have to be related to anomalies. But nevertheless, they tell you about the internal geometry. For example, the four-dimensional R-wedge-R term tells you about the canonical class of the base manifold B3 of this elliptic vibration. In other words, it tells you about the location of the branes and orientifold planes if you use these kind of topological terms. On the other hand, using geometric identities, you can link these canonical class for an elliptic vibration to the spectrum. Okay. For example, if you have no gauge groups, the elliptic vibration implies that the spectrum is linked to this coefficient A in front of the R-wedge-R term in this fashion. So these are the number of complex structure, Kähler, and so on. Some moduli. In other words, for such a genuine F-theory compactification, I assume here no gauge group, no chiral matter. It's not really phenomenologically appealing, but you get some link between the spectrum and the and some terms in the effective action, despite the fact that you have no anomalies. You can also include gauge groups, and this equation becomes a little bit more fancy, but again it relates these topological terms, the coefficients of these topological terms, to the spectrum. Okay. This is hard in 4 dimension because you have to distinguish the moduli fields if you want to evaluate this explicitly. And you can imagine that this is a complicated moduli space. However, you get some numeric coincidences which always have to be satisfied in such a consistent compactification. You have to understand the scalar potential, so fields can become light or heavy, so this can distort the story. But at the end of the day, the hope could be, or we can ask the question, are these new constraints which we did not understand yet from a 4-dimensional point of view, which go beyond anomalies, or is that just something which we cannot reliably address in each zeta? In any case, what we point out is that this kind of approach using topological terms not only helps to address constraints, but it can also help to understand F-theory heterotic duality in more general context. Okay, so you've seen that were quite 3 intensive parts, so let me come to the conclusion. The M-theory to F-theory limit is powerful. It involves a double-dimensional reduction. I pointed out that mapping the data from one to the other side can be non-trivial. I told you that Chern-Simons terms are very important to study the effective 4-dimensional theory, include loop corrections and so on. So loop corrections can map to classical corrections in this duality. I stressed that it's important to include warping effects in M-theory if you want to compute, say, alpha prime correction. In particular, we studied already the gauge coupling functions. And I stressed that the F-theory key data of the F-theory compactifications are encoded in topological terms and might lead to interesting constraints beyond anomalies. This is, of course, an open, wide field, and we hope to proceed on this. There are many open questions. For example, we heard already a little bit about M5 brane instantons, and what I want to stress is that M5 brane instantons also go very non-trivially through this duality, okay, which we will work out soon. And then here are some open questions which you can all read. Thank you very much.
Any questions? do you think that you can apply the same method for the calculation of alpha prime correction to Kähler potential? Not just stage free function.
Yes, probably yes. Yeah, I mean that's something we are thinking about. Of course, that's very exciting. The question is, here we actually solved the swap factor equation explicitly near such a brane geometry, right? I don't know how far these methods can be extended, how general we can make it. I mean, certainly tricks need to be invented to cover the full story. But I think it's a very neat story, because if you look closely, where the new physics come from is the fact that the swap factors actually peaked on this circle. On the circle where the 6 branes live. This was this kind of correction term, which is the key point to understanding this correction.
I have a question about the warping and the higher F terms. So I just wondering how much this can be extended to, relating to two things. One is to do with how do you get the topological Chern-Simons terms out of this, because the warp factor involves the metric.
Right, I just dropped this story. We also have this story in the paper.
Oh, you have the story in the paper?
Yeah.
Okay.
I just, for time reasons. So essentially the reason is you have to also extend the expansion of the M-theory 3 form, including this harmonic forms on this Taub-Nut space. And we matched this and we showed that this precisely gives the imaginary part in the Chern-Simons action.
Okay, the other question is like, how can you extend it to non-abelian, to the non-abelian case? Like, can you recreate like higher F terms, the non-abelian structure in them, like the trace?
We avoided this problem by switching on fluxes and Descartes only.
Yeah.
I got this question by some people before. It's probably possible, but it gets really messy. You have to dig really deep into the geometries of these Taub-Nut spaces and so on. But I expect that it's possible. Otherwise, it would be interesting to understand what goes wrong. Yeah.
I didn't get the point on the corrections to the gauge coupling. You say you have alpha prime corrections to the gauge coupling, and do you have this expression? Because it looks like an integral of the complicated expression. And
You mean this?
no, the alpha. You want to say the correction that you found? You were doing the warping.
So this is just the classical D7 brane result, which you know, of course.
Yes.
But,
then you said you were doing the when
you mean this one?
That one, yeah.
Right. No, I'm saying if I do the dimensional reduction, including a warp factor to 3 dimensions, the metric for the gauge fields in 3 dimension F wedge star F, so just the kinetic time of the U1s in 3 dimensions, has a warp factor inserted just from the metric. And then I just plug in this result of this analysis in here. You see that you get the leading term, which is just the volume, and then you get a sub-leading term which goes with the fluxes. So, and it all comes from solving this differential equation. It has some kind of boundary at infinity where it's just the leading term, and then some flux correction which is peaked on the brane. And I conclude alpha prime correction and suppress all the alpha primes. So there's LM here, right? So this map.
There are no more questions. Let's thank Thomas again.